Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussion of showing a lower bound for parity. So, what we showed earlier is that if we have a AC0 circuit which has mod 3 gates as well, then there is a multilinear polynomial which approximates the circuit quite well. Okay. So, now what we will show is the other direction, that if we have a multilinear polynomial, okay, of degree at most root n over f3, then on many inputs, so basically on 15% of the inputs, the polynomial disagrees with parity function, that is mod 2. Okay. And then we saw that if we combine these two, how we get a exponential lower bound on the size of a circuit, size of a constant depth circuit that computes mod 2. Okay. So, how do we go about proving this? So, here basically, so if you recall, so we have been talking about polynomials over f3, okay, but when we look at we are looking at Boolean functions, so why not just stick to f2, okay. So, what is the need to go to f3, okay, and this is where that need will arise basically, or this is the motivation why we need to go to f3. So, what we will do is we will look at the parity function slightly differently. Okay. So, what we will do is we will consider a mapping of 0 1 to minus 1 1. Okay. So, we will change our domain, and how do we change it? So, we map 0 to 1 and we map 1 to minus 1. Okay. Now, what happens as a result of this mapping? So, now as you can see that if I look at the following function, okay, okay. So, what is this mapping? So, we can actually define this using a simple linear transformation. So, this can be achieved by the linear transformation T of x going to 1 minus 2x. Okay. So, if x is equal to 0, then T of x is 1, and if x is equal to 1, then T of x is basically minus 1. Okay. So, this is a simple linear transformation and this can be achieved. Now, what happens as a result of this mapping? So, as a result of this mapping, what we have is that the parity function, that is mod 2 of x1 up to xn, now becomes okay, let me write it this way, product of yi's I going from 1 to n, where yi is equal to txi. Okay. And it is easy to see this because now look at this first. Okay. So, when is the mod function, when does the mod function evaluate to 0? The mod function evaluates to 0 if the sum is divisible by 2, that is basically if there are an even number of ones. So, if there are an even number of ones over here, now as a result of this mapping there will be an even number of minus ones over here. So, therefore, the product is basically 1, okay, and 0 goes to 1. So, this is fine, correct. So, if mod 2 evaluates to 0, if the left hand side evaluates to 0, then the right hand side evaluates to 1 as we require. Now the other direction is also clear. So if the left hand side evaluates to 1, so the left hand side will evaluate to 1 if there are an odd number of 1s over here. If there are an odd number of 1s over here, there are an odd number of minus 1s in this product. If there are an odd number of minus 1s in this product will evaluate to minus 1. So if the left hand side is equal to 1, the right hand side will be equal to minus 1 as required again. Okay. So essentially the entire essentially the reason why we go to GF3 is because we want to transform the this mod function into this computing product of n variables. That is the reason. And now we have kind of moved from F2 to F3. So here, well, we had 0 and 1, but now I can have basically, well, in this function I only have 1 and minus 1, but in general it is over the field F3 where I can have 0, 1 and minus 1. So minus 1 is the same as 2 basically in F3. Okay. So this is the basic reason. Now the question is, how does this help us? I mean, how does changing the modulus function into computing product help us? Okay. So this is where we will, so this is what we will see next. So what do we want to compute? So we want to show that the number of input on which P differs from product of, let me just write this as xi, product xi is at least 0.15 to the power of 2 to the power n. Okay, so let me define this set. So I will define this set A to be all inputs to the power n such that P of x, let us say, equals, well, when I say x, okay, let me just write this precisely, P of x1 up to xn equals product of xi's. Okay. So consider the following set. So let f be the set of all functions from a to minus 1, 0, 1. Okay. So we know that what is the cardinality of A? So the cardinality of F is, so each element can go to 3 different elements. A has A has some number of elements, so it is 3 to the power size of A. Okay. So we want to give a bound on the cardinality of A. Instead, what we will show, we will give a bound on F, and that will imply a bound on A by this equation. So how do we bound the number of functions that go from A to minus 1, 0, 1? So let us try to observe this. So what is a function? So basically a function over here is basically some multilinear polynomial. Okay, so it is some multilinear polynomial which is taking an input to this such that this P is equal to product of xi. Okay. So, okay, anything else? Okay. We will show that every function in f can be represented as a polynomial over f3 of degree at most what kind of degree do I want here? Okay. At most n plus root n by 2. So, now let us try to see this claim. So, why is this claim true? So, now let f be some function in capital F and let product of, let us say, some, let me use some other variable z i's I belonging to S be a monomial in F. Okay, so it consists of monomials. So take any one monomial. Now, if you want to bound the degree of every function, okay, then I have to show that every monomial basically will have degree at most this much. Okay. So, if S is already less than this, then we are done. So, if cardinality of S is already less than or equal to n plus root n by 2, we are done. Now, suppose the converse. Okay. So, suppose cardinality of S is greater than n plus root n by 2. Okay. So, what happens if S is greater than n plus root n by 2? It means that yeah, so basically I have a product of more than n plus root n by 2 variables over here. What I will do is, I will then we do the following, we will replace this product with another polynomial. So, we will replace this monomial with another polynomial whose degree will be bounded by n plus root n by 2. Okay. And what do we replace it with? So, we will replace it with the complement of these indices. So, I such that I does not belong to S times P of or no, here actually I have to take Z over here, I am dealing with Z's, P of Z1 up to Zn. Now, what happens if I do this? So, this is nothing but it is product of I not in S Zi times. So, by this, so because I am looking at a function in f and f basically is all inputs, I mean all functions which go from a to this, and a has this property, I can write this as product of I going from 1 to n Zi, and now by combining these two, this is actually exactly equal to this. Okay. Because all the i's which are not in S kind of gets cancelled off with their counterpart, and the indices that remain are the indices which are actually in S as required. Okay. And now what is the degree of this polynomial? So, what is the degree of this term over here. So let's call this as some, I don't know, so let's call this as P tilde. So degree of P tilde is, so here I have degree which is for indices that are not in S. S is greater than this, so complement of S will be n minus n plus root n by 2 times this. So what is the degree of P? So by our choice, so we have a polynomial of degree at most root n. Okay, so this is times, so it's a multiplying the thing, so degree gets added. Okay, and this, if you just solve this, so this inner term becomes n minus root n by 2 plus root n is again n plus root n by 2. Okay. So this is the reason why we wanted to replace the modulus function as in this product form, okay, because I want to be able to do this, and the reason why we have n plus root n by 2 this term is because this thing has to work out. I mean, in both cases the degree should be the same. Okay. So now we have this polynomial. So now I can just count. So what does this show? This shows that every function in f has degree at most this. So if f has degree at most this, so now I can count. So what is the cardinality of f now? So cardinality of f will be at most, so it is like all polynomials over GF3. Okay. So basically each variable can take 3 elements, and how many monomials, I mean the way I can pick a monomial is basically I can pick any I variables from a set of n variables. So it is n choose I, and there are the number of terms is, I mean the degree is bounded by n plus root n by 2. So this will be I going from 1 to n plus root n by 2. 3 raised to the power sigma I going from 0 up to n plus root n by, let me just write this a little bigger. Cardinality of f is at most 3 raised to the power sigma I going from 0 up to n plus root n by 2 of n choose I. Okay. And f is equal to 3 raised to the power I. So this implies that A is at most sigma I going from 0 up to n plus root n by 2 n choose I. Now what is the value of this summation over here? So if it actually went all the way up to n, I going from 0 up to n, this will basically be the this will basically be 2 to the power n, and you can actually show by, so one way is to show it by induction on n, that this is, for example, bounded by 0.85 into 2 to the power n. Okay. So different texts actually have different constant, but as long as this is a constant, it is good enough for us. Some constant less than 1, it is good enough for us. So what have we shown? That the number of inputs on which P and the product agrees is at most 0.85 into 2 to the power n. So therefore the number of points on which P and the product disagrees is at least 0.15 into 2 to the power n, and the product is nothing but the mod 2 function. Therefore basically, yeah, P of x is not equal to mod 2 of x on at least 2 to the power n inputs. Okay. So this completes the proof of this lemma. Okay. So now, yeah. So basically, what Razborov had showed in his paper in 87 is he had just shown this for mod 2. I mean, Razborov showed that mod 2 function is not in AC0. He didn't even consider the case when the circuit could have mod 3 gates. Then later on, actually Smolensky observed that even if you add any mod q gates where q is, let us say, co-prime to 2, okay, this entire thing works, because I can basically do that same thing. And not just for mod 2, if you take any p which is a prime, and if you take any q which is a another prime, then one can show that mod p cannot be computed by circuits which have mod q gates in addition to and or and not. Okay. So yeah, and not just, as I said, not just primes, it can also be generalized to prime powers. So just a remark. In fact, this is also a nice exercise to check. I mean, this is a nice exercise to go over the proof, that try to imitate the same proof for, let us say, prime powers and see what kind of changes one needs to do. Okay. So the result is true for prime powers as well. Okay. Okay. So this is basically where things stood in 1987. So the next obvious question was, what if I allow gates which are not prime powers? Okay, what if I allow gates which are product of 2 primes? The smallest such gate is the mod 6 gate. Okay, what if I have a circuit, an AC0 circuit, which has a mod 6 gate as well? What kind of functions can it not compute? For example, can one show that majority is not in this kind of circuit? Okay, so, and that was open. In fact, one couldn't even show, for example, functions in NP or even beyond that EXP and EXP, whether those functions do not admit or do not have a circuit that has AC0 along with a mod 2 gate. Okay, so this is just a parity function. I mean, here I have a very simple function for which I could prove a lower bound in a circuit which only has mod q gates, but the moment I add mod 6 gates, even very complicated functions which are NP, NEXP, EXP, we couldn't show a lower bound. Okay. So that is basically the result which Ryan Williams showed, that he showed that basically if you look at an ACC0 circuit, so there exists a function in NEXP, okay, which cannot be computed by ACC0. So ACC0 means the circuit can have any mod gates. Okay. So that is something that we will see in a couple of weeks' time. One other remark that is important over here is that what kind of lower bound are we giving over here? Okay. So the kind of lower bound that we are giving over here is that we have showed that mod 2 is, well, requires circuit of size. What is the bound? So what we have is one over epsilon, I think. Is it 1 over epsilon, or what was the result? Epsilon times 2 to the power n to the power 1 by 2d divided by 2. Okay. So let me just write it as this. So n to the power 1 over 2d. Okay. Now the question is, so here if you look at this function, so this is of course exponential, but it I mean I have a term 1 over 2d over here. Okay. So, another result that we will be proving is a similar result. So, it also gives a lower bound for the parity function. So, that was due to Hastad, but he actually gave a slightly better lower bound on the circuit size. Okay. So, what he showed is that there is a circuit. So, if I have a depth d circuit that computes parity, then it would require size 2 to the power n to the power 1 over d minus 1. Okay. So, 1 over d minus 1 is basically bigger than 1 over 2d. Okay. So, essentially his result actually gives a better bond, but then the flip side of it is that it only works for parity, it does not work for arbitrary mod p function. Okay. So, that is kind of the difference in the quantitative part of both these results. So, that is, yeah, we will do that next time. Okay. So, I will stop here. Okay. So, thank you.